So why is constructability so important to consider? It's all about identifying the most appropriate construction method or strategy early on so that we've got the right planning in place and that can be made in good time. It's understanding the risk and trying to design out risk and doing that right at the beginning of the project. It's about identifying temporary works that we're going to encounter across the project and perhaps establishing a temporary works register early on. It's producing some sketches and or perhaps drawings to communicate the concept of what or how and the process of what we're going to build, so that the project team can all understand and we'll all be on the same hymn sheet, as it were, so we can all strive and push in the right direction together and make the most out of the project that we've got ahead of us. As part of identifying the most appropriate strategy, this could involve how we can eliminate temporary works through smarter sequencing and using the existing structure or the permanent structure perhaps to take those temporary loadings. And actually that is a key focus on what we do at Andon. When we do concept design works on buildability, of trying to eliminate the temporary works and sequencing the permanent works or removal of the existing structure to eliminate temporary works, because this is where we can provide some significant savings across across the cost, time, and sometimes risk reduction. But that early planning associated with reviewing the constructability, that really enables better program and cost certainty for sure. But before we get to that stage of planning out what we're going to do and how, it is so important to understand the problem that we're trying to solve. That could be the obstacle or challenge that we need to overcome to make the project a success, i.e., how are we going to build the thing that we've been contracted to build? What things do we need to put in place and when? What obstacles do they present and how are we going to get over those? And it all comes down to my favorite acronym, which is GIGO, and that is garbage in and garbage out. If we're putting garbage into some kind of system or process, and this acronym is often used in IT and maths, but if we're putting some kind of garbage into a system or process, which could be how we're going to build things or the idea that we've got to solve a problem, if that is garbage going in, then we're only going to get a load of rubbish coming out the other end. It's really important to understand the problem that we're trying to solve and have as much knowledge about this problem so that the solution that's going to come out of the other end of this planning meeting or workshop or build it in a day workshop, which I sometimes see, that solution that comes out of there has really got to be born out of a thorough and fundamental understanding the problem at hand. And that does take some time. And sometimes it takes some spending money up front on site investigation and planning meetings, but they do pay dividends for sure. Okay, let's delve into some of those benefits of understanding these challenges that a project may bring early on, and understanding it and planning it sometimes as early as tender stage. So what we've got is chart here, and this is a chart from a really good design guide, which is Constructability, a guide to reducing temporary works, and that's published by the Temporary Works Forum. It's a very good read, and it's free on their website. It's a really good resource. So this chart that we've got here, on the left-hand side is where we have the project starts, and on the right-hand side we've got the project ending. Up the right-hand side we've got the cumulative cost of the project, and on the left we've got the level of the influence that we can have. So you can see at the beginning of the project we can almost do, especially if we're designing a new structure, there is constraints, but we have a lot of flexibility, and we can do almost what we want within the realms of the constraints that we have. So the level of influence is really, really high, and the cost of making amendments at this stage is very, very low. As we move along the project timeline across the bottom of that chart, then our level of influence decreases. What we can do decreases because it may be that now we are under planning constraints, so there's certain things we can and can't do, or we've brought certain subcontractors or principal contractors on board, who have already priced work, and changing that is going to cause a lot of aggro, so that the level of influence of what we can do decreases. And then also to mirror that inversely is the cost implications of making changes starts to increase. And as we see, as we go right across to the right-hand side of this chart, the cost increase is massive compared to how much influence we can have, because we may have already built the foundations and we can't change the layout of the columns now, for example, because the foundation's already laid. So that's going to have massive cost implications on that project. This is the design guide that I referenced there, which I took that chart from. It's a really good resource, but you can see that these publications that talk about constructability, temporary works is a key component which goes side by side. This is another good publication. It's by the Safe by Design work group, spearheaded by Steve Williams of Network Rail. And the words constructability and temporary works here are cropping up again. So they really go hand in hand, temporary works and constructability. As part of the constructability, there are other objectives we can also achieve if we're trying to be smart. Because after all, why not try to make things much more buildable whilst also reducing cost or making things quicker or even reducing risk? We should try and really shoot for the moon on these things early on in the project and see what we can come out with. So what we're trying to achieve and accomplish when looking at early stage constructability, or what we're producing something or building a constructability, what we're trying to do essentially is eliminate the temporary works if we can. And if we can't, we then reduce them as much as we can. We can try and make them more cost effective, improve the program, reduce carbon cost, or increase safety. Now, depending on the project that we have to hand, one or more of these particular items on this list may have a larger influence on the proposal, but it really depends what the driver is. So let's look at a couple of examples with this process in mind. So this is a project which is part of the Low Cross scheme, which was a subsidiary of Crossrail, and it was to provide step-free access across a number of stations. This project was in East London. This particular part of the project was to install a lift that took us from street level down to platform level. You can see some of the canopy of the station platform coming out there, the high level road on the left hand side and the platform on the right on the aerial image. And this retaining wall, which formed the back of the platform, looked a little bit like this. So it was a L-shaped retaining wall that had a shear key at the bottom and a masonry parapet on top. The canopy was removed, leaving the cantilevering retaining wall installed. The lift pit that was required to be installed to provide this step-free access would have been cutting off the toe of this retaining wall, which essentially removes its ability to provide stability. And the initial kind of tender scheme for this was to, well, if with this wall, if we're removing this toe, then we need to provide more ballast either side of this opening. And if we're going to be cutting that toe off, and that ballast was going to be in the guise of large concrete blocks. So the contractor thought, well, we'll stick a load of concrete blocks either side of this opening, create the opening, install the lift shaft, and then once that's installed, then we can remove the concrete box and move away. We took this scheme on when we were on board with the principal contractor at a later stage after tender, and we felt as though there could be some savings made here. So what we proposed to do is carry out some site investigation on the wall, in terms of understanding its structural composition and carrying out a more thorough and detailed analysis of the wall, also sleeving the piles where we're putting the lift shaft in, so we're removing less of the toe, which meant that we had a much lighter scheme. It was ended up being sleeving the piles and coring the holes, carrying out some SI, and then installing quite a lightweight whaler frame, which is propped back to some sheets there just to retain the soil that's underneath the platform that was remaining. So this is much lighter. It meant that we didn't have to install all those concrete blocks. So if we review that as part of our list that we had, so did we eliminate the temporary works? No, we didn't. We weren't able to do that because some kind of temporary support system was required to ensure stability. Did we reduce them as far as possible? Yes, we did. Instead of having lots of bulk lorries, which would also make the neighbours disturb the neighbours along that road, we significantly reduced the amount of the temporary works there by taking away the concrete blocks, which were quite substantial, and installed a much lighter weight scheme. Make them more cost effective? Yes, that's a big tick in that box. Improved program, and I would argue yes, because we've got much less logistics and moving vehicles coming into the area as opposed to the smaller frame. Reduce carbon costs potentially on vehicle movements. Increase safety, not so much increase, but maintained, I would say. It's important to maintain a high level of safety when we're working adjacent to railways. Okay, another couple of examples which were based around the Upper Holloway bridge replacement scheme. And I'm going to show you what this tower of children's building blocks has to do with the temporary works that we had in this scheme. So the first part of the scheme was to install a temporary, well, there's a services bridge, which you can see in the foreground of that photo. That services bridge would enable the existing services that went through the existing bridge to be diverted to go over that new services bridge, which meant that the existing bridge could then be demolished and then replaced with a brand spanking new one. A key part of that solution was where that existing bridge is in green, to remove the areas of the embankment which were adjacent to the wing walls, which are shown in brown on that plan, and which then enabled the construction of the foundations for the new services bridge. So to remove all of that earth, we needed to install a retaining wall solution, which we couldn't get around. We had to put something in to retain that soil. So we proposed a king post pile wall, which was on the lines that are shown in red there. And to install that king post pile wall, we needed a couple of excavators that were operating on the road of the existing bridge. And they were leaning over there, and they were leaning over an area which is shown in that star blue hatch, which was absolutely riddled with services, quite shallow, which those services would eventually be diverted onto the new service bridge. The existing proposal was to spread the load out using a reinforced concrete slab, because we're going to get some quite high pressures from the tracks of that machine, especially if it's leaning out, that far, and it's leaning onto its front track on its front toes. That's exactly where the high pressure is going to be. And so putting that reinforced concrete slab down to spread the load seems like a good idea. What we proposed was to use timber mats that spanned over the services and onto the masonry spandrel wall that was on the bridge. And this is where the children blocks come in. So the solution not only did away with the reinforced concrete slab and the loading of the services altogether, but it also stabilized that wall. So it's much like the building blocks. The wall was much more stable as there's a stabilizing load being applied. So it's much more difficult to push over. So if we stack those children blocks and we push them down from the top, trying to push them over from the side, it's a much more stable structure. And that's similar to what we were doing here. So we can review this against our list. So did we eliminate the temporary works? No, but we did reduce them as far as possible. Had we made it more cost effective compared to a temporary slab? Yes, we did. Improved program? Yes, tick. We didn't have to install a reinforced concrete slab and then remove it afterwards as well. Reduce carbon cost? I would say yes. Increase safety? Yes, we did in this instance, because we provide a stabilizing force for that wall as opposed to trying to push it over. We also did a very similar thing when the mobile crane came in to install that services bridge, putting that crane on top of the abutments, which were the abutments for the existing bridge, shown in green there, bringing the crane closer to the actual center of gravity of the crane lift, of the the services bridge lift. Get my words out this morning. Bringing them closer to that bridge means that the driver can be much closer to the lift operations that are going ahead. Also means that a smaller crane could be used, and less temporary works, less rigging time, rigging up a smaller crane. And that's not a new idea, by the way. It's not something that we've come up with at Andon. It's something that engineers have been doing for years. The pinnacles and the statues on Gothic architecture, that's some 12th century engineering right there. And we're using that knowledge which is already established, but employing it into a kind of more contemporary fashion. It's a kind of a hobby subject of mine, and there is a medieval engineering an Andon-led medieval engineering, not podcast, webinar on the YouTube channel. And so check that one out. But if we review that works as our list, then we've got eliminate temporary works. No, we couldn't. We couldn't eliminate temporary works. We needed to do something there. Reduce them as fast as possible. Yes, we had a smaller crane and make them more cost effective. Yes, we did. Improve the program. Yes, that would have been improved because we had a smaller crane as opposed to a larger crane sat further away. Reduce the carbon cost and marginal, I suppose, with the smaller crane. The key driver for me, though, is the increase in safety. By moving that crane closer to the lift, it's a smaller crane, it's a smaller radius, it's loading those abutments so they are providing additional stability. And the driver can see, you can see the cab there, he's looking directly out of his cab and right at that services bridge right in front of him. So it's an increase in safety. And that is a really good case study for driving this process of buildability. Okay, let's have a look at some deliverables and what this could look like. So if we look at the type of things that to be thinking about at this planning stage, then we're planning and thinking about the problems that may come up against, which is really going to help us in the long run. But what can we expect in terms of what sharing these ideas and what they look like? First of all, what I like to do is a very simple sketch by hand, sometimes on the back of an envelope, in a meeting or something like that. And these really help communicate the concepts of buildability. And we've got an example here, which kind of was cradle to grave, really, on the concept design of a basement propping scheme in Manchester. So we can see here we've got a couple of sketches which are done by my colleague James Dunlop, who's a manager in our Nottingham office. And he did a very good job here. He basically identified all of the constraints a part of the job and came up with a scheme which we felt best suited that proposal. And this was discussed, enabled the projects or the proposal to be quoted, and it identified, more importantly, issues and problems that the site team would come up against in putting this new basement in, which was quite difficult, really. It was an existing basement, and we were going deeper with our new basement, so it was quite a tricky job. So this was tabled, discussed with subcontractors or the principal contractor. And that early concept design sketches turned into more of a preliminary design after that. So these were more flesh on the bone, CAD drawings, working concept, if you like, which therefore enables a sequence and a program to be put together, which gives the client or contractor cost certainty or more cost certainty and program certainty, which is very important at this stage. And then following on from that, that's when you have the full finalized design, which comes at a later date. But going back to this early stage concept, it's very, very similar to what we had as our final stage. And that's because we spent time and we were given time at the beginning of the project, not an awful lot, but we were given some time at the beginning of the project to really delve deep and to understand the problems that we'd be coming up against. And as such, we had that idea bob on pretty much from the beginning. You can see the James's sketch there that we've got in the middle. It looks really quite similar, if not the same, as what we had when the actual works were going on site. And that's really what it's all about. It's understanding the problems and the constraints at the beginning to get the correct solution, so that we can all just push forward with that proposal going ahead into the scheme, and we're not doubling up on work. We've just got the right solution at the beginning, and it's really great to see these structures. This is a photo that I've taken in front of that structure, the landmark structure. It's really great to see these proposals going forward from the beginning, getting the right solution and taking that all the way through to the end. I'm certainly not saying that all the work that Andon did was worth all the credit for us. There was lots of others involved in that. So the credit's due to others on the project, Curtins as the structural engineer and Bowman Kirkland as the principal contractor, for sure, because that was a good project and a good case study for that constructability. Okay, so now how do we make sure structures are buildable? Yes, we are thinking about them earlier on, but what do we do when we come up against a problem? Such as the structure isn't designed for the kind of loadings that we expect from our proposed case. Here's a case study where we had two structures here, and one was Halo in Bristol, and one was Old Granada Studios in Manchester. So both these tasks were quite similar in regard that we had some plant required to operate on the permanent slabs, so the raised ground floor slabs, some larger plant, mutes, for example, and cherry pickers. But the slabs that they were operating on weren't strong enough to take the plant loadings required to build the superstructure. It may have been that these floors were designed for people walking around on them and not for large plant that is used to assist in erecting the superstructure. Typically, the stock response of when we're further down the line is, well, let's just put some backpropping in there to support the slab and provide that support to the permanent structure so that it can take the loadings from the proposed plant. But the assessment on the temporary works loadings on these structures resulting from those mutes and cherry pickers, that proved quite interesting in both cases. So the structure wasn't designed for those heavy loadings, so that meant, well, we'd probably be going down backpropping. But we thought, well, is there a better solution to this backpropping? We need to hang on a second and think about this. So we did some exploration. Critically, the slab hadn't been constructed yet. So therefore, we reviewed those loadings from the various plant and checked the new slab design and for bending, shear, deflection, etc. And we checked the punching shear on the columns and the column capacity. So we checked the whole lot, essentially. And we concluded that, yes, there were areas in this structure which failed due to the additional plant loading. So the initial conclusion was correct. But what we did identify that there was only certain areas of these structures that failed. So how about we strengthen these areas in the slab by adding additional bars and additional reinforcement, which we then do away with all the backpropping. And that's what we did. So following that conclusion, we produced this drawing. This one's for Old Granada Studios. And the solution removed the requirement for that backpropping and its associated costs of installation and hire and then also removal. But more importantly than that, in this particular job, the critical path of the project was kind of getting the basement finishes completed, and by removing the backpropping from the basement, that they could carry out the waterproof or finalizing waterproofing issues and finishes on the basement, which was a fantastic result. So the solution was very effective in speeding up the program and reducing the costs, whilst also maintaining the required margin of safety. It did take some forward planning, but you've really got to think ahead to get ahead of the game and make that design a slave to you and not you a slave to the design. So if we look at our list that we had against there, which we referenced earlier, did we eliminate the temporary works? Well, kind of. It's cheating a little bit, really. Yes, we did get rid of the propping, but we did include some additional reinforcement, which was kind of hidden from view, really, because it was cast in. So we reduced them as far as possible. We did make it more cost effective, improve the program, a big tick against that one, reduce carbon costs, marginal really, increase safety. No, not really. We more maintained the suitable levels of safety that we had in there. Okay, so it's another good example. So if we have to build temporary works, that is if we have explored options to try and reduce them when we've been sitting in our planning meetings and trying to figure out smarter ways of building our structures, and we come to the conclusion that no, the most viable way is to have some kind of temporary works, then the next option here is to try and reduce, right? So how can we make that process more slicker? We need to think about the erection and the dismantling process. It may be that a lot of constraints have changed during the time of the temporary works has been in, so that needs to be considered. Who's going to be putting it together and where? Is there heavy plant available to lift heavy sections, or will it be done by small plant or even by hand? That's important to think about in terms of buildability. Keep things simple if possible. What's going on around the temporary works during this process? Clash detection is the big one as well for the permanent works install. We need to make sure it's easy to build, for the temporary work side, but then we also don't want to just be kicking that can of difficult things to do and difficult jobs to do, which we all like to do sometimes, kick that can down the road and visit that in another few weeks' time. We don't want to make the permanent works an absolute pig to build as well. So we need to think about clash detection and what we can do there. And also, are there any off-the-shelf products that are designed specifically to solve this problem? We don't want to be trying to reinvent the wheel. We should be reviewing it and researching other areas of technology that we could utilize to make our project much slicker. This is a couple. I'm just going to throw up a couple of examples. So this is a modular system frame which we designed for a large-scale building stability scheme, which was the Bristol Beacon, formerly known as the Colston Hall project. This design was quite extensive. You can see there's a significant structure that we're supporting here. It was more like a facade retention scheme, but the facades were on pretty much all sides, and it was very difficult. So it was a facade retention scheme which enveloped the whole building really on the inside. But the modular frames you can see there on that fabrication drawing that we put together meant that they could be fabricated off-site, brought to site, lifted in, installed, and then away we go, like big building blocks, really. So that was something that can be employed. And you can see here some of the clash detection that went into the design development of this proposal, highlighting the temp and overlaying the permanent works to make sure that the solution that we've got from the beginning is the right solution from beginning to end. So we're not going back and revisiting things, which is just a total waste of time. Yeah, and you can see that more of that proposal going in. You can see the permanent works and temporary works working very nicely together on that project. On the smaller scale of things, there are other things we can do to make things easier to build. So we've got a capping beam propping solution here, where we are supporting this capping beam in the short term. The capping beam in the long term is actually going to be supported by those grey lines there, which you can see from this diagram. So that wall, that contiguous pile wall and capping beam are going to be supported pretty much continuously from one side to the other, which means they're not working an awfully hard to provide stability. However, in the temporary term, we need to think about the process of that structure being built. The contiguous pile walls are going to be installed, then the capping beam on top, and then we're going to do our reduced level dig. At which point we haven't got the ramp and we haven't got the slab inside, so we need to put some kind of propping to that wall, or could design, if the ground is suitable, we could design the contig pile wall and to cantilever completely from the basement level, which would remove the requirement for propping. So there's a few options there. In this case, the most viable option was to put some props into the top of the capping beam, but in doing that, the capping beam was spanning from prop to prop, which you can see there, as opposed to in its permanent case, it was just being pretty much continually supported. So it is working harder in its temporary term than it was in the permanent case. So it needed to have an assessment. It needed a strengthening and reinforcement in the side faces of the capping beams so it could span from one prop to the other, which all takes a bit of planning and takes a bit of time, but identifying those requirements early on means that we can build it right the first time, and we don't need to have a temporary whaler, for example, going along the face of that capping beam to deal with those temporary cases, because we've already missed the boat in slightly changing or slightly upping the bar size on the permanent works when we build that. Seeing as we had a hand in what that permanent capping beam would look like from the structural engineers, because we reviewed that and amended the bar size slightly, we could also detail some temporary or some pockets in the capping beam with holding down anchors, which would eliminate the sometimes difficult process of post drilling and fixing props to heavily reinforced capping beams. Drilling in a hole, hitting a bit of rebar, not getting the template quite right. And this way, with holding down anchors in pockets, meant that the beam could be offered up, the prop could be offered up to the pocket and fixed into the holding down anchors, and away we go, nice and slick and simple. So you can see that process in here. Another option here is of making things easier to build is more on the clash detection side. So these props going through doorways, or for example on On this slab here, we can see that we've got those props going through large parts of the slab, large spans of the slab, which means that when we are going back, once these props have been removed and repairing these holes, that we're doing them in places where you can lap reinforcement as opposed to putting them in areas where you'd have to use couplers for your rebar, which are very expensive. We can lap that reinforcement if we create a slightly bigger hole, or put them through doorways so we haven't got to put a make good hole whatsoever. These props in particular were going through the lift core. As such, the reinforcement was quite heavy in that area. So the make good patches would be quite difficult there. So it's important to get those in those areas where we could. There's another example on this project, which I'm not going to go into today, but it essentially was key to winning us the Constructability Award for the ICE in the Northwest Awards, and that was a composite soldier design. It was the development of this soldier, which was slim and pressed up against the wall and anchored to that existing wall, which enabled a significant reduction in the amount of concrete used in that basement, and also maximised the space that we had there. And so that is found on our YouTube channel as well, just as a shameless plug, really, of our YouTube channel again. So to sum up, really, on some of the key learning points that I've covered today, I know I've been kind of jumping from one thing to the other. I just wanted to give you a kind of a broad understanding of little tips and tricks that we can do, as well as some of the key driving information that is required to putting together a constructible project. One of the key takeaways is understanding the problem, and that is super important, and this process can take a little bit of time. It can be front heavy, so there more than likely will be money required to be spent at the front end, but that really does pay dividends later on. So that may be in the realms of getting some site investigation and understanding the structure that you're dealing with, but you can't get to the right solution unless you understand the problem. And that site investigation at the front end is really sometimes, and most of the time, in my opinion, essential in understanding the problem. Another key takeaway is that early consideration of constructability can save time, money, and save or reduce risk. And there may be ideas, big and small, already established in the industry and buildability, so use them to your advantage. There's a lot of good stuff out there, and so have a little look on some research around the subject that you're looking at. There may already be something out there off the shelf that is absolutely perfect for your particular issue that you have. But yeah, again, that importance of the thorough and fundamental understanding of the structure you're trying to build and the constraints is absolutely key. Okay, so more on the subject. There is loads of content out there on the internet, which is a good first port of call for just a quick Google, for example. But there's some very good published literature, which hopefully that takes you to. A really good source of information is the Temporary Works Forum website shown there, temporaryworks or twforum.org. And that's where that constructability guide lives. Really worth a good flick through there. The Safe by Design group publication I've shown there as well. There's the new British Standard, BS 5975, that is out now. I just realized that I've kept the old 2019 version in there, but there is a new version and that's out and in use. The Temporary Works publication by the ICE is a good all-rounder subject on temporary works. And then also, why not mention again our YouTube channel? There's loads of content on there for various items of temporary works and demolition, tips and tricks and all sorts of bits and bobs. So